All right, so we're picking up where we left off yesterday. We're looking at, still looking at the electric field. And in this second example, we still have a dipole with a positive charge here, a distance a along the negative x-axis, and a negative charge here, a distance a from the origin along the positive x-axis. And the question this time is, what's the electric field up here at a point P that's a distance b here from the origin? So what's basically we're asking, what's the electric field along the y-axis when we get a distance b away?
Mr. Marcus,
Yeah.
when you said we had school yesterday, after lesson yesterday, you're telling me we had school?
No, Ollie, you know what he means.
Yeah, the lecture.
Yeah,
the last lecture
well,
we
I'm just
were
making
at
sure
was
because
yesterday.
you
You're
confused
right.
me. That's it.
It was last week.
I just have to make sure, you know.
No, we didn't have school yesterday.
No.
Okay. So I also want to make sure I go over. These are the objectives we're looking at for this lecture, right? This is and this example specifically is for point number 3 here. We want to calculate the magnitude and direction of the electric field produced by 2 or more point charges. Right, that's one thing that's going to come up pretty often in this class. You know, it's helpful to be aware of what objective we're looking at when we look at it. And before we try to answer this, I want to see if we can make what we can predict about it. All right. So what we'll do is take a quick look at what the electric field of a dipole looks like and see if we can make any predictions about what our answer is going to be. Here's dipole. So what you can use there's a lot of apps out there that'll show you the electric field of various charges, including a dipole. And remember, a dipole is just a positive and a negative charge close to each other. So if we want to figure out what the electric field is somewhere on the y-axis above the center line here, right above the origin, can we make a good prediction about what direction the electric field is going to be?
It's going
Yes.
to be towards the.
What's it going to be?
It's going to be towards the negative, towards the blue. Okay.
Towards the left, did you say?
Yeah, no, towards the right.
Towards the right, right? If we look at all the arrows that are on the y-axis, right, it's always pointing exactly to the right. So we can predict that the electric field will be to the right, or in the positive I hat direction. Is there anything else? Any other predictions you think we can make about what the electric field is going to look like? Maybe how it depends on B, that distance above the dipole.
You're still sharing your screen, so we can't really see your notes zoomed in anymore.
Yeah, no, right. That's fine. I know. I'm going to go back to the notes in a second. I just want to say if we're looking at this field, right? If we go up along the y-axis, the field lines get farther and farther apart from each other. Does that tell us anything about what we can expect for our answer of how the electric field is going to depend on the value B?
It'll get weaker?
It should get weaker, right? Because the electric field lines are farther and farther apart as we get farther and farther away. So we would expect as B gets bigger, electric field gets smaller or weaker. And that kind of makes sense too as well, right? Whenever we get farther away from our charge, the electric field is going to get weaker. So it can be helpful to make these predictions and keep them in mind. And we'll check our answer at the end and see if those predictions match up with reality or with our answer anyway. Okay. So let's see, here we go. Well, how should I start?
Well, wouldn't you first start with either one of the
Superposition.
Yeah.
For electric field.
start with first the Q, the big Q or the small Q, and then you go.
Yeah, so we figure out the field from each of these charges one at a time, right? And that is using the superposition principle, right? We just add together the field from this charge and from that charge. So the electric field we're going to be looking for is just going to be equal to, if we call this one, 1 and this one 2, our electric field is just going to be the electric field from 1 plus the electric field from 2. Okay. And how are we going to get, what's the big physics principle that we're going to use to get the electric field?
I
Coulomb.
don't know the equation.
Yeah, the equation, right? That equation has a name. Yeah, somebody said it. Coulomb's law.
Coulomb's law, yeah.
Right. So let me put down Coulomb's law again here for reference. Right. It's going to be. Well, I'll put it with the superposition principle, right? Because we're summing over each charge, right? In this case, I is going from 1 to 2 because we have 2 charges. Over each distance squared times each unit vector. All right, so we'll apply this equation twice because we have 2 charges that we're looking at. Okay, so let's start. We'll find E1 and E2, and then we'll plug in things that we can plug in for and see what we get. And I'll probably have to figure out what my angles are and what my R hat is, and I'll try to do that as I go along. But let's see what I can do so far. So E1, right? So the charge from this one, I start with K. What's my QI for charge 1?
Q.
Yeah, Q, right? This capital Q, and it's positive. Let's see, over R squared. So R in this case, right? The distance
From that to P.
from Q to point P.
Is the square root of like A minus B or B minus A, something like that.
Almost.
Square root of A plus B. Oh, A squared plus B squared.
Yeah, there you go, right? So R1,
Oh yeah.
that's just Pythagorean theorem, right? R1 is the square root of A squared plus B squared. Right? This is just a right triangle. So R1 squared is just A squared plus B squared. Right, if R1 is the square root of A squared plus B squared, R1 is just A squared plus B squared. And then we have this Ri hat here, right? So we have to figure out what that is. And that's usually, I think, at least for me, it's always kind of the most confusing piece. But the way to kind of remember what to plug in for that in terms of I hat and J hat, we know that this R1 is going to be the cosine of the first angle times I hat, the angle that R vector makes with the positive x-axis, plus the sine of the angle times J hat. Okay, so R1, or sorry, the angle here, right? This is the angle that first R vector makes with the x-axis, right? So that's angle 1 there. Now, how are we going to figure out what that angle is in terms of basically A's and B's, right? A's and B's are the given lengths. So we have to write this angle somehow in terms of A's and B's. Any ideas how to do that? I think trigonometry.
Tangent, something, I forgot.
Isn't sine is y over r or something? Yeah, it's y over r.
The sine is this over, well,
B over
yeah.
R.
Remember, we can go all the way back to SOHCAHTOA, right?
Opposite over hypotenuse. Opposite over
the
hypotenuse.
sine is going to be, yeah, so let's write this. What do we get for the sine? Is the opposite, so B
So B over r.
over the hypotenuse, right? And we don't want to write it as R, because that's not a
Oh,
given.
A squared plus
A
B
squared plus B
squared.
squared.
We would write it over A squared plus B squared, square rooted, right? Because it's R, not R squared.
Right.
So I'll put it to the 1/2 power. Okay, so that would be the sine of our angle 1. And then cosine will do something similar. What would I get for the cosine of that?
A over.
A over a squared plus b squared to the 1/2.
Right, because we're looking at the opposite or the adjacent over the hypotenuse, right? So this distance over that distance. So that is A over A squared plus B squared to the 1/2. Questions about that? I think we're good with those. So that means our R1 hat, it works out to be, well, and I'll put what we got here. Yeah, let me write down what we get for R1 hat. So it's the cosine of theta times I hat. So A over A squared plus B squared to the 1/2 I hat plus B over A squared plus B squared to the 1/2 J hat. Right, so I'm plugging these values for sine and cosine into this definition of our unit vector, or how to write a unit vector in terms of our components. So that means when I plug in, right, so when I plug this in over here, because right, this still has an R1 hat, we get E1, or that first, the electric field from the first charge, is going to be, well, let me combine the common factors. There's a KQ. So both of these terms are divided by A squared plus B squared to the 1/2. And we also have an A squared plus B squared down here.
To the power of 3 over 2.
So what does that work out to be for our?
To the power of 3 over 2.
Yeah, to the power of 3/2, right? Because we have this A squared plus B squared times another A squared plus B squared to the 1/2. And then what we're left with is AI hat plus B J hat. All right. So we've kind of done the work now of figuring out what that R hat vector really is, right? Basically, what's this direction? And we figured out all the, what the distances are, and we plugged it in. So we've got our E1 vector. So our E2, and let me put a star next to this so we can add it to what we get for E2. Our E2 vector is going to be pretty similar, right? We've got K. I'm going back to Coulomb's law here now. What's my second Q?
Little Q.
Negative Q?
Yeah, it's this charge, right? So it's negative capital Q.
Oh.
And the R squared this time, what's the distance of point P from the negative Q charge?
The same thing.
Yeah, same thing, right? It's the same distance. It's still the square root of A squared plus B squared, right? It's the same right triangle, just kind of flipped over. So we have the same denominator. If we square that, we get A squared plus B squared. And so now we have to look at what our R2 hat is. And we do it kind of the same way as we did over here. It's going to look pretty similar. There's only one little difference. We got to be careful about that. So we get the same answer, then it's going to cancel out completely and we'll have no electric field. So this time we have to look at the cosine of the second angle and the sine of the second angle. And you might think, and you wouldn't be that wrong if you say, okay, well, look, these are kind of the same angle here, right? Theta 1 and theta 2.
Right.
But not according to the way we kind of define things. What should theta 2 really be?
Should be the angle minus 180.
Yeah, right, because we always want our angle to be the angle that the vector makes with the positive x-axis.
Oh.
So this angle here is theta 2.
So
Go ahead.
So what would we say theta 2 is like? Well, never mind. Just go. I guess.
No, that's a good question. We can relate, like, we don't want to have theta 2 in there as well because we can relate it to theta 1, right? So we can get rid of a variable if we can relate theta 2 to theta 1.
So that will make the cosine negative, but the sine positive
Yeah.
still.
Yeah, it will, right? Because theta 2 is 180 minus theta 1. So that does mean that the cosine of theta 2 is going to be the negative of the cosine of theta 1. And the sine of theta 2 is just going to equal the same thing, right? The sine of theta 1. And you can, if you don't believe me there, go back and check your trig identities. I don't want to take too much time to go through that.
Or the unit circle.
What's that?
Said or the unit circle.
Or the unit circle, right? Exactly. Yeah, exactly. Okay, so that means we can pretty quickly get because we already found the sine and the cosine of theta 1, right? So that means we can plug right in for R2. Cosine of theta 2 times I hat. So it's just going to be the negative of what we got for here. This was theta 1. So minus A over A squared plus B squared to the 1/2 for the I hat. And then for the j hat, the signs are going to be the same. So the j hat term is going to be exactly the same. B over A squared plus B squared to the 1/2. So now we can plug that in. And we get let me keep the same terms here. So I'm gonna let me say it's KQ. No, I guess I'll pull that. So it's negative KQ over A squared plus B squared. And then just like before, right, we have a squared plus B squared to the 1/2 in both denominators. So that gives us a 3/2 down here. Times what we have left here this time is minus AI hat. Plus BJ. So that's our E2. And now we're just about done. We're going to see that we're going to get some terms canceling. So our electric field, and I'll write this out, we're looking, just remember the electric field is really, we can find it at any point whatsoever. We're really looking for the electric field at the point 0B, right? So that's going to equal. Now, when we add these two together, what terms do we have left? We're going to have a KQ over A squared plus B squared, the 3/2.
Oh, so you're gonna have two of the BJ's and no I's. And no
Well,
I.
careful though, because in this one, remember this minus sign here. So when we add them together, we've got A hat minus.
All the way around. Two I hats and
Right.
and-
So
and
the
no-
I hats add together so that we get two of them.
right.
So we have 2A times KQ over that denominator times I hat. And for the J hats, now we have our coefficient times B J hat, and then we have minus our coefficient times B J hat. So the J hats cancel out. All right, so this would be our electric field at that point. So just the last thing we want to do is check if our predictions were right. Is our electric field in the positive I hat direction?
Yes, sir.
No.
Well, yes.
Oh, yeah, we got negative. Did I do some math wrong there?
Yeah, it's supposed. Wait,
I
it's
don't
supposed to be
think.
positive. Wait, no.
You're right. So
Yeah, it's
yeah,
supposed to be.
it is supposed to be positive, right? Because we had this coefficient times a I hat minus, right? So we really are adding those together. So this is positive. So that's another good reason to make predictions and check it, because then if you make a mistake, that's a good way to catch it.
So why is the field positive if there's a negative? If there's a negative charge?
Right. That's a good question. Well, if you're over here, right? If we put a positive charge here,
Right.
so the field is going to point in the direction that a positive charge is going to feel the force. And it's going to be pushed to the right from this force, right? Away from charge Q,
Yes.
because it's being repelled. So charge Q is going to tend to push it to the right, upwards as well, but to the right in that
Mhm.
direction. But then this minus Q charge, that's negative, that's going to pull a charge over here towards it, right? So
Yes.
both of these charges are tending to push a positive charge here to the right.
Okay. So, okay. So the sign would be, so the test charge will always have to be positive. It can be
Yeah, you
negative.
assume the test charge is positive, right? When you're drawing your electric field, and it just works because then if we happen to put a negative charge there, it would just be forced the other way.
Yeah.
Right. So a positive test charge will move along the electric field lines or be forced in the direction of the electric field lines, and a negative test charge would just go in the opposite direction.
Okay.
And we can also see that our second prediction works as well, right? E gets weaker with larger B. The easy way to make sure that we can, or the way we can tell that, right? B is in the denominator here. So the bigger B is, the bigger our denominator, and the smaller our electric field. So our predictions seem like they work. Any other questions about this example?